Hey, welcome back, Shayla area. Welcome back to note video number 8 in Unit 2. Today we're going to talk about the history of the periodic table, so how we got this tool that we call the periodic table, and we're going to talk about the parts of an atom in a little bit more detail, at least how those parts of the atom relate to the periodic table. So where did the periodic table come from? Because it's not like it's always been here. So around the mid-1800s, there were people out there knew about 60 different elements. They knew that there were these substances that the whole Earth seemed to be made of. And if you could break down any other kind of materials, you would get down to these known substances. So by all intents and purposes, what we call today elements. So they knew about 60 of them, which wasn't too bad. They knew roughly 2/3 of the elements that were out there. And there was not a whole lot of technology back then. But what they didn't know was how to organize them. It's like 60 random, completely random things. Nobody could figure out what they had kind of in common or how you could categorize them. They would talk about them in these kind of like loose groupings, but there was no way that but the groupings kind of overlapped. They just didn't really know what to do with them. And this guy obsessed about it. Dmitri Mendeleev. He was a Russian scientist, and he knew that nature had patterns, and it seemed very odd that there would be something so fundamental about nature that didn't have a pattern associated with it. So he knew that there must be a pattern out there, and he just obsessed all the time. He did his other work and things like that, but any kind of downtime, he was thinking about the periodic table of elements. Or thinking about the elements. It wasn't the periodic table yet. And he is the guy who figured out the structure of the periodic table. So it probably seems to you that the periodic table is just a list of letters and these are just the elements. But once you know the patterns for why the table is laid out the way that it is, you can actually start to use it as a tool, because that's what it should be. It's meant to be a tool. So the word periodic actually means repeating pattern. And there's all kinds of patterns in the periodic table. Depending on what direction you're going, one thing will change. And you go a different direction, a different thing will change. They're organized by things that they have in common. And as the story goes, he obsessed about this so much that he never did come up with the answer, except one night while he was sleeping, he had a dream where all of the elements were kind of like swimming around in his field of view, and they settled into this nice orderly structure. And he jumped up from his dream and he grabbed a piece of paper and he scribbled it down, and then he started to really look at it the next day, and it seemed to make sense. And believe it or not, that's the story of how we have the periodic table. So what he did was he put the elements in order of mass. Like I said, we knew there were 60 different things, and we knew a lot about them. So we knew how much, we'll say, an atom of this material would weigh, or what the mass of it would be. And so he ordered them by mass, and he had done this before, but it just makes a line of 60 things. But now, this time around, he would kind of make a break at the end, sort of like hitting enter if you're typing, and bring it down to the next line. He arranged it so that the columns, the ones that were going up and down, all had similar properties. Like, for example, the column all the way on the left in today's periodic table, that entire column, if you drop any of them in water, they explode. They react with water pretty violently, with the slight exception of hydrogen at the top. All the metals, though, underneath hydrogen, they don't like being in water very much. Now, it didn't quite work out, because when you would hit like enter and come down to the next line and you'd start to enter them in by mass, you would get to a family where the next element that you knew about didn't fit into those kind of characteristics, like exploding in water. So part of the brilliance of Dmitri Mendeleev's plan was he skipped those. It would be like hitting spacebar. whenever he was going. And eventually he would get to a family that this element did have something in common with, and he'd put it there. And then he'd keep going. And if the next family, if the next column or the next family had the next element's kind of properties, he'd put the next one there. But if not, he'd skip it until he found the column that it did. And this was the brilliance, because when he proposed all of this, he understood what these patterns should be like so well, even though it didn't, like, the periodic table didn't even exist, that he had the gumption to make those empty spaces, and he said, you know what, we're going to discover what goes in there. It's something that we haven't found yet. And surprisingly or not, over the next few decades, every single one of the spaces that Dmitri Mendeleev left in the periodic table had been discovered and isolated, and then we knew something about it, and look, it fit like a puzzle right into that empty spot that he left. Now, there were a couple of spots that things didn't quite go so well. It didn't quite make sense. It seemed like some things were like out of order. We'll, so to speak, we'll call those the outliers. But he had almost all of them right where they were supposed to go. That's pretty amazing. And this is what his very first periodic table looked like. I know it doesn't look anything like you would think the periodic table looks like now, but it's kind of on its side. If you kind of take it and tilt your head to one side, that kind of makes a little bit more sense with what you're used to seeing. Can't really do it on here. I'd take it and kind of tilt the screen sideways so that this one was on top. So that these two were on the top of the page. And then along comes this guy. His name is Henry Moseley. Notice he actually did not grow to be very old. He actually went to war during the First World War and ended up dying in battle. But before he went to war, he did something that revolutionized chemistry. He discovered a method of being able to take one of those pure substances and actually measuring how many protons there were in an atom. And when he did this and he compared it to Mendeleev's table, he kind of reorganized the table. So instead of them going as Dmitri laid them out in order of increasing mass, he ordered them by how many protons they had, or their proton number. Today we call this their atomic number. And this ended up switching around a few of the outliers that were in Mendeleev's table, and then it all made perfect sense. Kind of fixed everything. But when Dmitri was working on this, we didn't have this bit of information. We knew how much an atom, like its mass of it, sort of how much it weighed, but we couldn't break it down by actual individual particles like protons, neutrons, and electrons. So when Moseley figured out how to do it by proton, it went in, it fixed those little ones. So look through the periodic table and see if you can figure out where Mendeleev had a couple of them wrong. See if you can find a spot where when you move up the periodic table, and I don't mean like up towards the top of the page, but when you're going by atomic number, like 1, 2, 3, 4, 5, when you get to the next one, look for a couple where the next element actually is lighter than the one that came before it, where it's less massive. And those would be the ones that were out of order in Mendeleev's. If you can find one, go ahead and send it to me with an email. It'd be worth some experience points for your character. So what's going on inside these atoms? Well, as we just talked about, there are a few stats, and they're all laid out in the periodic table for you. The periodic table tells you everything you'd pretty much ever want to know, once you know how to read it. So this number in the upper left-hand corner of the box of any of the elements is called the atomic number. This is the number of protons that is in the element. Now, in an element that doesn't have any charge, an element that's balanced, the number of electrons and the number of protons is always going to be the same. So we'll say in this element of nitrogen, if things are going to be balanced, well, if we have 7 fingers, 3, 4, 5, 6, 7, I guess we also need 7 toes. 2, 3, 4, 5, 6, 7. So if we have that, then we're balanced, because each finger balances out a toe. And then you're going to have no charge for the atom. Now, if something goes wrong, and we lose a finger or we lose a toe, now we're not balanced anymore. And you call an atom that's not balanced, or an atom with a charge, an ion. So here's a new vocab term. So if every proton in an atom gives the atom a +1 charge, and every electron gives an atom a -1 charge, you put them together and you get to 0. But if you take one away, now they're not balanced anymore. So in this case we have 1, 2, 3, 4, 5, 6, 7 electrons, and now 1, 2, 3, 4, 5, 6. Ah, that's a bad example. You'll find out later in a little bit. Bad example. Let me wipe all these out. Hit this button. All right, so let's try this again. So if you have 7 protons, 1, 2, 3, 4, 5, 6, 7, and instead of having 7 electrons, 2, 3, 4, 5, 6, instead of 7 you only have 6, you're not balanced. You don't have one here. This one's missing. So this would be an ion that would be a +1 ion, because while these would cancel out, you'd be left with this one, and it would be a +1 ion of nitrogen. Well, what if we did it a little bit different? And instead of only having 6, we could have this 8. So now, in this case, these ones all cancel out, and we're left with a -1 charge. So that would be a -1 nitrogen atom. And you can have multiples. You can have +3, +4, -6. But most of the time, atoms out there are balanced and have no charge. The mass number is not one of the numbers, not one of the numbers that you actually see in here. So we're going to learn about this number next, but this particular vocab term is not technically this number. It's close, but not technically it. The mass number is the total number of protons and neutrons in an atom. So the atomic number, this number up here, is the number of protons. The mass number is the number of protons and neutrons added together. This number down here is actually something called the atomic mass. And it's close to the mass number. Maybe you'll see the difference between them when I'm done explaining. So the atomic mass is the average mass number in any given sample of an element. Not all atoms of an element are exactly the same. All atoms of any given element, we'll say carbon, will always have 6 protons. They all have to have 6 protons. It's the number of protons that determines what the actual, which element the atom belongs to. You change the number of protons in an atom, you have a completely new element. You change the number of electrons or neutrons, that doesn't matter. The number of protons makes it the element that it is. So that's this number. You can have different numbers of electrons, as we just saw. Those are ions. Or you can have different numbers of neutrons. And if you have different numbers of neutrons, it doesn't change the element, but it makes the element heavier or lighter, as we say. It's more massive or less massive, bigger or smaller, but not really. Don't think of it like that for volume, because the nucleus of the atom doesn't really do anything to the volume of the atom. That's the electron cloud. But if you have different numbers of neutrons, it's called an isotope. I'm going to try to illustrate this here, what this actually means. So imagine that we have this carbon. There are isotopes of carbon that range from mass number from the number 8 to the number 16. So it'd be kind of like your, let's say every single human being on the planet was an identical twin. We were all exactly the same, and we were all named Tom. everybody on the planet. And now we started kind of taking all those people, taking all those Toms, and some of them were going to be a little bit different. We're going to make them just a little bit taller, like an inch. So most of them are going to be one height. We're going to make some of the other ones about an inch taller. Well, we'll say that most of them are the carbon-12. So most of the Toms on the planet are like this. Some of the Toms on the planet are now going to be this tall. Some of the Toms on the planet are going to be a little bit shorter. Some are going to be a little bit shorter. These would be like the low ones. This would be like carbon-8s. These ones would be like the carbon-12s. And it can go all the way up to a really big carbon-16, although that's pretty rare. Well, as it turns out, (98.93% of all of the carbon on the planet. So all of the atoms are carbon on the planet, which is a lot of atoms because life is carbon-based. So everything that's alive has atoms of carbon in it and is actually structured on carbon. So almost all the carbon has a mass number of 12, which means it has 6 protons and it has 6 neutrons. So to have a mass number of 12, it's the total number of protons and neutrons together. So if we know the protons are 6 and we know the total is 12, we can say it has 6 neutrons. Little tiny bit. So we'll say the number of, so Tom's is everybody on the planet, and we'll say there's another one, Jerry. Jerry is another version. It's an inch taller version of Tom. But the number of Jerrys that we have are like the number of people that are the Sherpas in Himalayas. There's not a lot of them. So that's 1%. 1% of all of the carbons. And then let's say that somewhere along the lines there's somebody who's actually, maybe their skin's bright purple. We'll call them Violet. We'll say Violet is out there. She's like the only one. Maybe there's 3 or 4 of them. These are the carbon-14s. And carbon-14 makes up 1 in a trillion atoms of carbon. So if you have a trillion atoms of carbon, one of them will be carbon-14. You may have heard of carbon-14 because we use carbon-14 a lot in like dating of things, dating like how old, artifacts are, maybe dinosaur bones, those kinds of things. We can figure out actually within a couple thousand years of how old something is using carbon-14 dating. And the reason that we can use this for like a timing dating system is because these 2 atoms of carbon, carbon-12 and carbon-13, are stable. They will last forever. Every other isotope of carbon, so 8, 9, 10, 11, 14, 15, 16, they're all radioactive, which means they don't stick around forever. They actually fall apart. The atom is unstable, and one of the reasons that the atom can be unstable is, I don't know if you remember, we talked about this before when we talked about the parts of the atom and where they're found, is that in that nucleus you have all of these protons, right? And protons are all positively charged, and that doesn't make them all want to be in the same place. Because remember, if you have two north poles of a magnet and you try to put them together, it's really hard to get them to touch. They do not want to be next to each other. And we have all of the positive parts of an atom crammed into one tiny little central space, and I'm telling you, they don't like it. They want to fly apart from each other. The neutrons kind of provide some padding in there, and kind of a little bit of separation between those protons, and it kind of makes it so that they will hang out. They don't like it, but they're not mad and explosive about it. When you mess that up, though, if you start to pull some of those neutrons out, or you start to put too many neutrons in, it can change that dynamic, and it makes the protons unstable, and they start shooting out of the nucleus, and that's what we call a radioactive atom. So anyway, the radioactive ones don't stick around, and carbon-14 is one of those. So if we can figure out how many it started with, and we know how many are left, we can actually tell exactly how old that piece of stone or whatever it is. But if I were to take all of those trillion atoms in whatever it is that I'm holding, and I measured the mass of every single one of them individually and then divided them by a trillion, we would get the mass number of 12.011. So that's what we use for the atomic mass. Anytime you want to do any calculations with, carbon, and you want to know how much 10,000 carbon atoms weighs, if you had a sample of 10,000 carbon atoms, you can actually use this number and figure out an exact amount of what those carbon atoms would weigh. By the way, I know I have you guys learn a lot of units. I want to be clear that you do not have to know this unit. You're never going to have to do anything with an AMU as far as converting from one unit to another. I know we do that with a lot of other units, but that's not one of them. So there are some quick check questions. Not going to give you the answers, obviously, but I'll kind of walk you through them. So how many electrons does a neutral atom of oxygen have? So if you look back, remember that one of those numbers up here tells you how many protons the oxygen atom has, and if it's neutral, you know how many electrons you need to balance that out. This one down here is making an ion. So if you have an atom of oxygen and it's not stable and it's not balanced, it doesn't have a neutral charge, it actually has a charge of a -2. I want to know how many electrons it will have. I have to think about that one a little bit. And then, based on what you can see up here in this periodic table slice, I want to know if I had a party and I invited 1 trillion oxygen atoms, would more oxygen atoms show up that were oxygen 17, or would more oxygen atoms show up that were oxygen 15? I guess to start answering that question, most of the oxygen atoms that would show up would be what? That would be the most common. Good. The most common isotope of oxygen would have a mass of 16, because that's pretty much what that number is. So if the most common oxygen atom that shows up in my party out of 1 trillion has a mass number of 16, I want to know if the next most common isotope that showed up was 17 or 15. And you can figure that out with the periodic table. All right, that leads us to the booby trap that's on the history of the periodic table and the parts of the atom and how they relate to the periodic table. There's 10 questions. Good luck.